As the additional vapor is condensed in the condenser and flows into the receiver, the temperature of the liquid in the receiver increases. The condenser temperature control loop senses the increase in temperature in the receiver. This control loop then adjusts the louvers in the path of the forced air from the fans in the condenser to cool the increased amount of vapors. In addition, the external reflux control loop senses the temperature increase in the tower and reacts by increasing the flow of external reflux to the tower. The increased reflux flow causes more condensation to take place in the tower. As a result, the temperature in the tower decreases. So far, we've looked at the effects of increasing the bottom temperature set point. The control system for the distillation process in our example responds to a decrease in the bottom temperature set point by decreasing the flow of steam to the reboiler. The control loops then respond to the change that has occurred in the tower's energy balance. Distillation process control systems can consist of many different combinations of control loops. The control system for a particular process is designed to meet the requirements for that process. But regardless of the process, a change in a process variable can disrupt the system's material and energy balances. Control loops are designed to restore the balances, but operators need to be aware of changes in their systems so that they can help ensure that products meet specification. Changes in the external reflux that flows to a distillation tower can affect the composition of the tower's products. When external reflux enters the tower, its lightest portion vaporizes and flows out of the tower with the other overhead vapors. The rest of the external reflux flows down the tower. The reflux helps to condense the heavier components of the vapors in the tower. A decrease in the amount of reflux entering the tower means that more of the heavier components remain as vapors and reach the condenser, where they are condensed and sent to the overhead receiver. The increase in vapors in the tower also raises the temperature in the tower. Now, an increase in the amount of reflux entering the tower causes more condensation to take place in the tower. As a result, more of the feed's heavier components are condensed and will flow back down the tower. And since more vapor is condensed, the temperature in the tower decreases. The tower's control system will react to either an increase or decrease in the tower's temperature. When there's an increase in temperature, the external reflux control loop senses the change and then increases the flow of external reflux to the tower. The increased flow of reflux condenses more of the vapors in the tower, and the temperature in the tower decreases. When the external reflux control loop senses a decrease in the temperature, it decreases the flow of reflux to the tower. In some distillation systems, the external reflux flow is kept constant. The amount of condensation is varied by changing the temperature of the reflux. Introducing cooler reflux into the tower has the same effect on product composition as increasing the flow of reflux to the tower. In this topic, we looked at how a tower's control system responds to changes in bottom temperature. We also looked at how product composition can be affected by changes in external reflux. Now try some practice questions that relate to this material. In this system, the bottom temperature is controlled by adjusting steam flow to a stab-in reboiler. This is accomplished by the bottom temperature control loop. Now, an increase in the amount of reflux entering the tower causes more condensation to take place in the tower. As a result, more of the feed's heavier components are condensed and will flow back down the tower. And since more vapor is condensed, the temperature in the tower decreases. The requirements for a product are sometimes called product specifications or specs. A spec is a value or a range of values for a physical property that is required for a product. Products are routinely tested to ensure that the specs are met. Testing can be done by direct composition measurement or by indirect composition measurement. Direct composition measurements are analyses that allow personnel to directly observe the percentages of components contained in a product. One type of instrument that is commonly used to perform direct composition measurements is a process chromatograph. A process chromatograph analyzes a product and provides a readout of the component percentages. The measurements made by the chromatograph can be compared against specs to see if any adjustments are needed to ensure that the product meets specifications. Indirect composition measurements are analyses in which one measured property is used as an indicator of another property. In other words, the measurement of a property is used to determine product composition. One common indirect measurement is boiling temperature. For example, since the boiling points of the components in a feed mixture are known, the components in a product can be indirectly identified by their boiling points. When a product is tested, its composition can be indirectly measured by recording the temperatures at which the different components in the product boil. Product specs are set by the demands of downstream processes and by the marketplace. Products must meet certain quality standards. For example, a downstream process may require a feed of predetermined quality. Sales contracts and marketing practices also require distillation systems to produce products that meet certain quality standards. Exceeding product specs or producing better quality product than is required is known as product giveaway. When product giveaway occurs, both product and energy are wasted. For example, a facility uses more utilities, such as fuel, than necessary. And in many cases, customers may not be able to use the products. Doing this can reduce a facility's profit margin. Product composition measurements are made to make sure that the products of a distillation system are on spec. For example, the tower represented here separates a feed that contains methylcyclopentane, or MCP, and cyclohexane, or CYC6. The MCP is the lighter component of the feed, and it is removed as the overhead product. The heavier CYC6 is the bottoms product. In this example, the spec for the bottoms product is 0% MCP. In other words, all of the MCP should be removed as overhead product. The spec for the overhead product is less than 5% CYC6. To help maintain product specs, samples of the products are taken and sent to the lab on a regular basis. Indirect composition measurements are then performed to determine the percentages of MCP and CYC6 in the products. Distillation tests are run on the products to obtain their initial and final boiling points. If the initial boiling point of the bottoms product is lower than normal, it indicates that there is some MCP in the bottoms product, so the bottoms product is off-spec. If the final boiling point of the overhead product is higher than normal, it indicates that the tower is too hot. When the tower is too hot, an abnormal amount of CYC6 is sent overhead with the MCP. If there is more than 5% CYC6 in the overhead product, the product is off-spec. If the tower is too hot, the bottom temperature could be too high. If so, it should be decreased slightly. Decreasing the bottom temperature allows more of the heavier component, which is CYC6, to remain in the bottoms product. This action may decrease the amount of CYC6 passing overhead, and it should bring the products back to spec. If the percentage of CYC6 in the overhead product falls too far below 4%, there is a danger of some MCP remaining in the bottoms product. To bring the products back to spec, the bottom temperature should be increased slightly. This ensures that as much of the lighter component as possible is boiled out of the bottoms liquid. In general, changes in a tower's operation should be made in small increments. Gradual changes allow time for the process to react and minimize fluctuations that are caused by overshooting the set point. Now, product specs and the way they're controlled involve a variety of factors. One of these factors is process lag. Process lag is the time between making a change in tower operations and having the adjustment take full effect in the tower. In some larger towers, the process lag is long, and it may take up to several hours for results to develop. In smaller towers, the process lag may be shorter, and a result may be seen more quickly. Well, in this topic, we looked at product composition. Specifically, we looked at product specifications and how these specs can be tested and maintained. Now try some practice questions that relate to this material. The requirements for a product are sometimes called product specifications or specs. A spec is a value or a range of values for a physical property that is required for a product. Now, product specs and the way they're controlled involve a variety of factors. One of these factors is process lag. Process lag is the time between making a change in tower operations and having the adjustment take full effect in the tower.